Since this will be our last lesson devoted entirely to puzzles and pure logic, we've saved a real barn burner for our finale. The problem is known as the Muddy Children puzzle, for reasons that will become clear momentarily. Our puzzles in this lesson are a bit different from those we have seen to this point. In a typical logic puzzle, you're presented with certain facts or statements about the world, and your task is to work out what follows logically from them. In today's puzzles, we're instead asked to draw logical conclusions based on what other people were able to infer from information they were given. That being the case, I need to add a word of caution before we dive into our puzzles. You should always assume that the characters in the puzzles are perfect logicians. They will see any point that can be deduced from the information they have, regardless of how subtle the point is. With that in mind, let me present the puzzle of the Muddy Children in an especially dramatic form. Here we go. 100 girls were playing outside. It had rained recently, and as a result, all of the children had mud on their faces. One of the adults supervising them decided to teach them a lesson in logic and arranged them in a large circle. Every child could see the faces of all the other children, but no child could see her own face. The adult tells them that at least one of them has a muddy face. She then tells them that at 5-minute intervals, they should step forward if they know that their own face is muddy. In other words, after having told them that at least one child has a muddy face, she wants them to wait 5 minutes to give everyone time to work out the logic of the situation, and then to step forward if they know they have a muddy face. They then get another 5 minutes to reassess the situation. If at the end of another 5 minutes they know whether they have a muddy face, then they get another opportunity to step forward. As the time passes, will any of the children ever step forward? And just to head off possible answers that are definitely not in the spirit of things, you should assume that no one has a mirror and that they are not allowed to touch their face to see if there's mud there. They have to do this by logic alone. This is a truly brilliant puzzle, since it seems like nothing much at all is going to happen. Each child sees 99 muddy faces in front of her. So what possible difference does it make that the adult told them that at least one of them has a muddy face? They already knew that. And yet it does make a difference, for reasons that will become clear as we go along. In fact, something truly amazing will happen as the children work through the logic of the situation. Now, this is actually a very difficult puzzle. In fact, we'll break our usual pattern of asking you to solve it now so that we can build up to the solution through 2 other, simpler versions of the puzzle. And let's start by trying essentially the same problem with just 2 children. Here's what such a puzzle would look like. It seems that there were 2 sisters who were playing outside in the yard. It had rained recently, so there was quite a bit of mud. When they go into the house, their father has them stand facing each other. Each child can see the other's face, but not her own. Their father tells them that at least one of them has a muddy face. He then says, "Step forward if you know right now whether or not your own face is muddy." Neither girl steps forward. After a pause, the father repeats his request. "Step forward if you know right now whether or not your own face is muddy." What happens this time? This one is quite a bit more manageable than our opener, so see what you can do with it. Pause the video here if you want to try this yourself. Good luck. Any success? To get a grip on what's happening here, let's look at it from the perspective of one of the children. We'll call her Anne, and we'll call the other girl Beth. Let's consider the possibilities. Could it be that Anne's face is muddy, but Beth's face is clean? Well, if that were the case, then Anne would reason like this. I can see that Beth's face is clean, but my father said that at least one of us has a muddy face. If Beth has a clean face, then I must be the one with the muddy face, so I will step forward. But we know that Anne didn't step forward, and therefore she did not reason like this. The only conclusion is that this scenario is impossible. Of course, similar reasoning tells us that it can't be that Anne's face is clean while Beth's face is muddy. For then, Beth would have used the reasoning we just described to conclude that her own face is muddy and would therefore have stepped forward. Since she did not step forward, this scenario is also eliminated. In other words, if only one child has a muddy face, then that child would have realized it and would have stepped forward. Since neither child stepped forward, we know that, actually, they must both have muddy faces. So what happens when their father makes his request the second time? Let's once more look at it from Anne's perspective. She will process everything that's happened and think, at first, I saw that Beth had a muddy face. But my father only said that at least one of us has a muddy face, so at that point, I didn't really know whether my own face was muddy, so I didn't step forward. But wait a second. Why didn't Beth step forward a moment ago? She went through the same reasoning I did. If she saw that my face was clean, then she would have known her face was muddy and would have stepped forward. Since she didn't, it must be that she sees that my face is also muddy. So this time I will step forward. Of course, Beth will go through precisely the same reasoning. So now we can answer the question. What happens when the father makes his request the second time? The answer is that both girls step forward. I think that's a very nice puzzle. Anne and Beth don't learn anything directly from their father's statement, but they do learn something from how the other one responded to that statement. In particular, they learn something about what the other girl knows. Having considered the scenario for 2 children, let's move on to 3. So let's suppose that the sister's friend Cora stopped by for a visit. Once again, all 3 played in the mud. When they went inside, the sister's father had them stand in a triangle. Once more, each child could see the faces of the other 2, but not her own. The father tells them that at least one of the girls has a muddy face. He then says, if you know right now whether your own face is muddy, then please step forward. All 3 girls stay where they are. He repeats his request. If you know right now whether your own face is muddy, then please step forward. Once again, all 3 girls remain where they are. So the father tries one more time. If you know right now whether your own face is muddy, then please step forward. And this time, all 3 girls step forward, laughing because they now realize that they all have muddy faces. Can you work out how they came to that conclusion? As usual, pause the video here if you want to try this yourself. I think you'll find that an extension of our prior reasoning will get the job done. As a place to start, let's suppose that Anne is the only child with a muddy face. Then she would think, I can see that both Beth and Cora have clean faces, and since my father said that at least one person has a muddy face, it must be me. So I'll step forward. Since she did not step forward, we know that this scenario is not correct. Of course, Beth and Cora will go through the same reasoning. Since no one stepped forward after the first time their father made the request, we now know that at least 2 of the girls have muddy faces. The 3 children know that too. Now we come to the second round. What do they learn when no one steps forward the second time? Would Anne now know that she has a muddy face? Yes, because she would think, is it possible that I'm the only one who doesn't have a muddy face? If I were, then Beth and Cora would both be looking at one clean face and one muddy face. But they know, just as I do, that at least 2 of us have muddy faces. Since they know this, but since they each only see one muddy face, they would know that their own face must be muddy. But neither of them step forward in response to my father's second request. It must be that we all see 2 muddy faces, which implies that all 3 of us are muddy. And that's why all 3 girls step forward when the father makes his request the third time. Let's recap. When no one steps forward in response to their father's first request, all 3 girls know not only that there are at least 2 muddy faces among them, but also that all 3 girls have figured that out for themselves. They bring that with them in response to their father's second request, and when no one steps forward in response to that request either, they know that they all have muddy faces. Are you ready now to handle the version with 100 children? The puzzle is on screen for you to review. If you want to take another stab at it, this would be a good time to pause the video. Okay, here we go. We know that if there were only one muddy face among them, that person would quickly figure out that she's the only one. She would see 99 clean faces, and since she knows that somebody has a muddy face, she would deduce that it was her. So after 5 minutes, she would step forward. If there were exactly 2 muddy faces among them, then those 2 children would see 98 clean faces and 1 muddy face. After 5 minutes, neither would know about her own muddy face, but then each would reason that if her own face were clean, then the other one would be looking at 99 clean faces and would then know that she must herself have a dirty face. So when no one steps forward after 5 minutes, they know that this scenario is not the case. So after 10 minutes, the 2 kids with muddy faces will step forward. And if there are exactly 3 muddy faces, well, then those 3 will be looking at 97 clean faces and 2 muddy faces. Those 3 will already have worked out that if her own face were clean, then the other 2 would be looking at 98 clean faces and 1 muddy face. And each would know that in that scenario, those 2 would step forward after 10 minutes. So when 10 minutes comes and goes with no one stepping forward, then those 3 will all know they have a muddy face. After 15 minutes, all 3 will step forward. Do you see the point? We can very quickly extend this reasoning to the case of exactly 4 muddy faces. In that case, those 4 kids would be looking at 96 clean faces and 3 muddy faces. Each would reason that if her own face were clean, then after 15 minutes, all 3 of the others would step forward. So when no one steps forward after 15 minutes, all 4 will step forward after 20. And now we can answer the question. What happens is this. After 99 intervals of 5 minutes, all of the children will have remained motionless. And then, after 500 minutes, which, if you're interested, is actually 8 hours and 20 minutes later, all 100 kids will step forward at the same time. It's almost unbelievable. I've worked through that solution many times, and I still don't quite believe it. But the logic is unassailable. Let's consider some more puzzles of this sort. Here's one I've always liked. This time, we have Dave and Enid. Enid has 3 children, and she tells Dave that if you multiply their ages together, you get 36. Enid then says, "It's interesting, Dave, but the sum of my kids' ages is the same as your son's age." Dave shakes his head and says that's not enough information to determine the ages of the 3 children. Enid pauses for a second and says, "Come to think of it, my oldest son likes to play the violin." At this point, Dave was able to work out the ages of Enid's children. Can you? Just to clarify an important point, you can assume that we are only measuring the children's ages in years. In other words, each child's age is a whole number. You don't have to worry about any child being 4.5 or anything like that. We'll take the standard brief pause so you can mull this over. Any luck? Well, perhaps a logical place to start is with the fact that we have 3 kids whose ages multiply out to 36. There are only so many ways for this to happen, and we could just list them all. This might be a good time to remind you that this is a logic puzzle. We don't worry about things like the plausibility of having 1-year-old twins at the same time that you have a 36-year-old child. We care about mathematical possibilities only. We next learn that the sum of the ages is the same as Dave's son's age. I think we can assume that Dave knows his own son's age. And yet, this was not enough to solve the problem. But wait a minute. Most of those triples we listed have a unique sum. In other words, 1, 1, 36 is the only triple that sums to 38, and 1, 2, 18 is the only triple that sums to 21. Since Dave could not yet solve the problem, we look for triples that have the same sum. The only 2 such triples are 166 and 229, which both sum to 13. If the ages of Enid's children were anything other than those triples, then Dave would have been able to solve the problem at this point. The last piece of information was that Enid's oldest plays the violin. That implies that Enid has an oldest child. But if the correct triple were 166, then she would not have an oldest. We wouldn't know who Enid was talking about in saying that her oldest plays the violin. So it must be that the ages are 2 to 9, and that's the answer to the puzzle. Very nice. As it happens, though, that was meant as a warm-up for a more difficult puzzle. This puzzle is famous among mathematicians, but fair warning, it's pretty hard. Here it is. Fred was visiting his friend Gina. They were at a park watching a large group of children playing. Fred asks, "Are those all your children?" Gina replies that there are 4 families of children playing. She says, "My family is the largest, my brother's family is smaller, my sister's family is smaller still, and my cousin's is the smallest of all." If you care to count, there are fewer than 18 kids total. Gina then added, "It's a funny thing, but if you take the number of kids in each family and multiply those numbers together, the result is my house number, which I know you know." Fred thought for a moment and commented that he needed more information to work out the number of children in each family. He asks, "Does your cousin's family consist of a single child?" Gina replied, and Fred was then able to work out the number of kids in each family. Can you do likewise? This is another of those delightful puzzles where it's unclear even how to begin. But if you mull it over for a while, you might realize that you have more information than you think. Okay, let's see what we can do. Fred initially has 2 pieces of information. The total number of kids is less than 18, and the number of kids in each family is different. What can we infer from this? Well, I think the best way to start is to work out what the smallest number could be. If the smallest family had 3 children, then the smallest total number of children occurs when the numbers are 3, 4, 5, and 6, which adds up to exactly 18. That's too many. So the smallest family has no more than 2 children. Now we can start listing some possibilities. Let's suppose the smallest family has just 2 kids. Then we need 4 different numbers, with the smallest being 2, whose sum is less than 18. With a little experimentation, we find that there are only 7 such sequences, and here they are. We also know that the product of the 4 numbers is Gina's house number, which Fred knows. Of course, we don't know the house number, but that doesn't matter. What matters is that Fred knows it. If you care to check, the result of multiplying the 4 digits in each of those 7 possibilities is always greater than 120, with the exception of 2, 3, 4, 5, where you get exactly 120. Why is that important? Because we now consider the possibilities where the smallest family has 1 child. There are a lot of them, but with a little experimentation, you can quickly show that the largest product is going to occur for the sequences 1, 3, 5, 8 and 1, 4, 5, 6, which both multiply out to 120. Remember that it's the cousin's family that has the smallest number of children. Now, suppose the house number is larger than 120. Then Fred would have known that the cousin's family has 2 children. And if the house number is smaller than 120, then Fred would have known that the cousin's family has 1 child. Either way, he would not have needed to ask if the cousin's family had only a single child. Since he did ask, we know that the house number must be 120. What happened next? Fred asked if the cousin's family had only a single child, and Gina answered. Fred was then able to rattle off the correct sequence. But if Gina had answered yes, then Fred would not have known whether the correct sequence was 1, 3, 5, 8 or 1, 4, 5, 6. Since Fred did know, it must be that Gina said no, meaning that the cousin's family has more than 1 child. And Fred then knew that the 4 families had 2, 3, 4, and 5 kids respectively. As we've seen, puzzles of this sort can become tremendously complicated, but I have to admit that I find them enormously satisfying. There's probably a life lesson buried in them too. Sometimes you have more information than you think you have. With careful attention to detail and a lot of patience and clear thinking, you can accomplish quite a lot from a very minimal starting point. Let me conclude with one more puzzle in this genre. It's quite difficult, so you might find it a bit more trouble than it's worth to work through all the possibilities. But I urge you to stick around to enjoy the solution nevertheless, just to marvel at the ingenuity with which this puzzle was constructed. Here we go. This puzzle takes place on the same island of knights and knaves that we've seen before, so let me remind you that knights only make true statements and knaves only make false statements. Now, imagine a criminal trial has taken place. The prosecutor said, "The defendant is guilty and has committed other crimes in the past." The defense attorney replied, "The defendant is innocent and the prosecutor is a knave." The judge then asked a question whose answer he already knew. One of the attorneys answered the question, and this revealed to the judge whether that attorney was a knight or a knave, because the judge knew whether the attorney answered truthfully or falsely. From this information, it turned out that the judge was also able to determine whether the defendant was innocent or guilty. A reporter present at the trial described all of this to a logician. The logician found he had insufficient information to determine whether the defendant was guilty. He asked the reporter, if the other attorney had answered the question instead, would the judge then have known whether the defendant was guilty? The reporter thought for a while and replied, "I really don't know. In fact, there's no way of knowing." The logician replied, "Oh, good. Now I know whether the defendant was innocent or guilty. So now I leave it with you. Was the defendant innocent or guilty?" If you want to have fun with that one, then take a few minutes now to work through it. This one requires some patience. Let's try working our way through the various possibilities. We have 4 cases to consider. One of the 2 attorneys answered the question, and his answer revealed whether he was a knight or a knave. So, first, let's suppose the prosecutor answered and revealed himself to be a knight. Since the prosecutor said the defendant was guilty, the judge would now know the defendant was guilty. The judge would also know that the defense attorney was a knave. Moving on, it might be that the prosecutor answered and revealed that he was a knave. But in this case, the judge could not have determined whether or not the defendant was guilty. Keep in mind that the prosecutor said the defendant is guilty and has committed other crimes in the past. It could be that the defendant really is guilty but has never committed other crimes in the past. That would make the prosecutor's statement false, which is consistent with his being a knave. Or it could be that the defendant is innocent after all. That would also make the prosecutor's statement false. Now let's suppose the defense attorney answered. If the defense attorney answered and revealed that he was a knight, then the judge would know the defendant was innocent since the defense attorney said that he was. The judge would also know the prosecutor was a knave. And finally, suppose the defense attorney answered and revealed himself to be a knave. In this case, the defense attorney's statement is false. But as with our previous case, this would imply that at least one part of the defense attorney's "and" statement is false. And that means either it's false that the defendant is innocent, or it's false that the prosecutor is a knave. If the first statement is false, the defendant is guilty. If the second statement is false, then the defendant is again guilty because the prosecutor would then be a knight and he claimed the defendant was guilty. Either way, the judge would now know the defendant was guilty. Let's record these findings in a table. The key point is that if the defense attorney had answered, then the judge would know if the defendant were guilty or innocent, but if the prosecutor had answered, he might not have known. That's as far as we can go with the first part of the story. But now we consider the exchange between the reporter and the logician. The reporter was at the trial and therefore knew which attorney answered. Suppose the prosecutor had answered the judge's question. Then, when the logician asked about what would have happened had the other attorney answered, the reporter would have thought, let's see, I know that the prosecutor answered the question, so the other is the defense attorney. Having analyzed the cases, I know that if the defense attorney had answered, the judge would have known if the defendant was innocent or guilty. So the answer to the logician's question is yes. But the reporter didn't say yes. He said there was no way of knowing. It follows that it was the defense attorney who answered the judge's question, thereby revealing whether he was a knight or a knave. Now, could he have revealed himself to be a knight? No, for suppose he did. Then the reporter would have reasoned, if the defense attorney revealed himself to be a knight, then the prosecutor is a knave. But our analysis shows that if the prosecutor answered the question and is a knave, then the judge could not have determined whether the defendant was guilty or innocent. So the answer to the logician's question is no. But the reporter didn't say no. Again, he said there was no way of knowing. The only way this is possible is if the defense attorney revealed himself to be a knave. And since the defense attorney is a knave, our analysis of the cases reveals that the defendant is guilty, and that's the solution to the puzzle. Honestly, I think that can be savored just as a piece of poetry. See you next time.